Alright, so this question asks, what is the difference in pH for a 0.1 molar solution of oxalic acid versus a 2.0 times 10 to the negative 7th molar solution of HBr? Now I put right here that this is actually a problem dealing with a concentrated but weak acid versus a dilute but strong acid, being HBr. I put some steps starting right here of what I kind of think of each time that I approach one of these problems. If you know that you're going to be setting up and solving a rice table problem, I typically start out by figuring out what the equation is. You can do this by looking at oxalic acid. You probably don't know what that compound looks like. HBr is easy because they wrote it out for you. But oxalic acid, what you're going to do is you're going to go to your formula sheet that will be provided for you, and you're going to find oxalic acid right here. You can see what the acid is, HO2C2O2H, and its conjugate base. So the acid is going to be on the left side of the equation, conjugate base on the right side, and we're going to have H2 on the reactant side with the acid and the hydronium ion, or H3O plus on the right side, or the product side. Same is going to go for HBr, reactant side, product side. And the next thing I look at is right here on number 2, is if the acid is strong or weak. Now, HBr, I can look at the Ka value and say, wow, that is even stronger than HCl, which is right here. So it's a very strong acid. Oxalic acid, I see that it's 5.4 times 10 to the negative 7th, which is smaller than 1, and which is smaller than the hydronium ion Ka value, which means the weak acid. So I know that I'm going to highlight them here. I'm going to say oxalic acid is weak, and I'll do that in pink, and then hydrobromic acid, or HBr, is strong. I'll do that in red. Next, I decide if the acid is dilute enough to consider the auto-ionization of water. Now, what I mean by that is, remember in class how we covered the fact that water is auto-ionizing all the time. All that means is that you have water reacting with itself. So that means that you got, I'll do this like OChem, but you got this electron pair grabbing a hydrogen off of this H2O molecule, and you get H3O plus OH minus. So this H2O becomes the hydroxide ion because it loses a hydrogen, and this H2O becomes the hydronium ion because it gains a hydrogen. Or it auto-ionizes with itself, and it undergoes an acid-base reaction all the time. Now, most of the time, we ignore this if our solution is concentrated enough. For example, if our solution was 0.1 molar, and this is of oxalic acid, we are going to ignore it in that situation. But in this situation where we have only 2.0 times 10 to the negative 7th molar of HBr, that's such a small concentration that the auto-ionization of water is going to make a difference. And how do we know that? Because we know that the Kw value equals 1 times 10 to the negative 14th. And what we know is that Kw equals H3O plus hydronium ion concentration times the hydroxide ion concentration. And what that means is that each of these concentrations must be the square root of 1 times 10 to the negative 14th, right? So 1 times 10 to the negative 14th, equals, I'm just going to do H plus. It's the same thing as H3O plus, right? OH minus. Or 1 times 10 to the negative 14th equals x squared. Okay, so now we just square x, and we are going to get 1 times 10 to the negative 7th equals x. And that is going to equal both the H plus and the OH minus concentration. Now, when we say that something is dilute enough, we mean that this is typically the power that we look at. Now this, if it was like some big number, 5, 6, 7, and it was times 10 to the negative 5th or negative 4th, it might not make a difference. It might be big enough where it won't show up in sig figs. However, it will normally be pretty obvious, and there's a way to tell if you should have ignored it later on that I'll try to point out. But pretty much any time that one of your concentrations is near the value of 1 times 10 to the negative 7th molar, you're going to have to consider the auto ionization of water. And normally we do not use a weak acid or like oxalic acid. We typically wouldn't add that we wouldn't dilute that because it's a weak acid that we're going to need a lot of it. Strong acids don't typically need that much depending on what we're trying to do, and so we do dilute them sometimes. So that's how we tell if we're going to need to consider auto ionization of water. And then I put right here that if it's a polyprotic acid, depending on if it's strong or weak, that will tell us if we need to focus on the first hydrogen that dissociates or the second or even possibly the third if it's an extremely strong acid. And I covered this in 2 previous videos. But for this problem, I'm going to write both rice tables so you can see them kind of solved together at the same time. Now, yes, I already wrote this down to conserve some time. Right, so here's our oxalic acid, and we'll start with that. So this problem says that we need to find the pH for a 0.1 molar solution. I'm going to line this up a little bit more so I'm not writing on the lines. So I start with a 0.1 molar solution. I know that I ignore H2O for all these because it's a pure liquid. And I also need to look up the Ka value for oxalic acid. So I'm going to go over here, and it's 5.4 times 10 to the negative 7th. So Ka equals 5.4 times 10 to the negative 7th. Alright. Because this is a weak yet somewhat concentrated acid, this is really going to be solved just like any other simple rice table problem that we've done thus far. We're going to start out with 0 of the conjugate base and 0 of the hydronium ion concentration. We're going to lose X and gain X. We're going to get 0.1 at equilibrium. We get 0.1 minus X, and X for both the conjugate base and the hydronium ion concentration. Now let me write like a dividing line right here. Sorry if that bugs you if it's kind of slanted, but so right now I know that I'm going to set up and solve for X. So I get my Ka value, which is 5.4 times 10 to the negative 2nd, not 7th, sorry, equals products over reactants, right? So X squared over 0.1 minus X. Now, I would actually advise skipping, like pausing the video right here or even beforehand and then solving it yourself, and then come back and watch how we solve it and see if you did it right. It's always best to test yourself first. So what I'm going to do is I multiply all this over, and when I do that, 5.4 times 10 to the negative 7th times 0.1, I'm actually just going to get, it's going to move over 1 decimal place, 0.0054 or you could write 5.45 times 10 to the negative third, minus 0.4 times 10 to the negative second x equals x squared. Now I'm just going to set this up to, sorry, yeah, I'm not solving for x, I'm actually going to put it into the quadratic formula. But I get 0 equals x squared plus 5.4 times 10 to the negative second x minus 0.0054. Now pause it, put it into your quadratic formula, and then see what you get for x. You should get x equals negative 0.105. We know that that's not going to be right. And then it should be positive 0.0513. Alright, 129, whatever. And now this value is going to go in to the H3O plus concentration because, right, these are just simply x, so they will equal the same value for x, which is this. And the question asks what the difference in pH is for a 0.1 molar solution of oxalic acid and then this hydrobromic acid. So what we're going to have to do is we're going to have to find the pH of both and subtract them from each other. Sorry, I say a lot, but the pH we know is going to equal the negative log of the H plus concentration, and we know that the H plus concentration is 0.05129, and that is going to give us, it should give us a pH of 1.29 pH. Alright, now I'm going to stop this video so that it's faster to upload, and then I'll move on to hydrobromic acid.